Hello students and friends. In this video I'm going to talk about the stereochemistry of carbon molecules, particularly the wedge and dash structure, which I have already told in my previous video. So we know that when carbon forms four bonds, then these four bonds are directed towards the corners of a tetrahedron as shown over here. We often use a wedge and dash structure where we know that the two bonds which are shown by normal straight lines are in the plane of the paper. The wedge shows that the bond is coming towards the observer, and the dash shows that the bond is going away from the observer. In this video I will also show you the three-dimensional models so that you get a much more clear picture. And then, as you know, that it is often desirable to draw something called as Fischer projections, in which we convert a three-dimensional structure into a two-dimensional structure as shown over here by a cross. These cross type of structures are known as Fischer projections. So this same molecule which I have shown over here with two normal bonds and wedge and dash, this can be rotated in such a way that we have got two wedges and two dashes, and now the two wedges are the two bonds uh, coming towards the observer, and these dashes are the bonds going away from the observer. So this same thing can be drawn in this way, that the horizontal line shows the bonds going towards the observer, and the vertical bonds showing the bonds going away from the observer. So this three-dimensional structure that you see here is equivalent to this. These two bonds are pointing towards the observer, the red and the white, the red and the yellow, sorry, and the white and the black are going away from the observer. Now the point is that if we transform this Fischer representation and just interchange or just change the positions of some of the atoms or groups, then do we get the equivalent structure, that means the structure representing the same molecule, or do we get the structure of a different molecule? So whether the structures are equivalent or they are non-equivalent. Now to explain this point further, if you look at the two structures that I have drawn, 1 and 2, then you will see that here the red and the yellow have been turned by 180 degrees, so that the red and yellow, as you can see, they have been turned by 180 degrees. The white and black also have been turned by 180 degrees. So see, so this is what I have done. I have made two 180 degree transformations. And when you do two 180 degree transformations, they are allowed, and that gives you equivalent structures. That means 1 and 2 are representing the same molecule. They are not representing two different molecules. So two 180 degree transformations are allowed. But if you go from 1 to 3, then you will find that the red and yellow, they are still occupying the same positions, but I have made one 180 degree transformation between the white and the black. So this is a 180 degree, but there has been only one 180 degree transformation. And now this one 180 degree transformation is not allowed, which means that 1 and 3, they do not represent the same molecule, but they represent actually the mirror images, which are non-superimposable, and therefore they are different molecules and they represent enantiomers. So this is one thing that you have to understand. And now I will show this to you with the help of the models. Okay. So now you can see that I've shown you that the white and the black, see the white and the black. Now if you see the white and the black, see the white and the black, the white and the black, they are going away from me. They are going away from me. White and black are going away from me, and the yellow and the red are pointing towards me. So so if I make 180-degree transformation, so I'm making 180-degree transformation, so that you should see that the white and the black, which are in this way, now you see I make a 180-degree transformation, and now in this position you see that the yellow is towards my left, and the red is towards my right. Now if I make a 180-degree transformation like this, if I make a 180-degree transformation like this, so that now uh, the there has been a second 180-degree transformation as well. So now the red and the yellow, they have also been transformed by 180 degrees when I've made one transformation for the black and the white. So two 180-degree transformations take place simultaneously. Here the red and the yellow are pointing towards me, and the white and the black are going, white and the black, they are going away from me. So if I make a 180-degree transformation like this, then the other 180-degree transformation also takes place simultaneously. That means two 180-degree transformations are allowed, and they actually give you the same equivalent structure, right? Okay. So now let's see that what is the other possibility, right? So so what we find is that two 180 degree transformations are allowed, right? So that is what I have shown over here, that two 180-degree transformations are allowed, right? See this, right? So two 180-degree transformations are allowed, but one 180-degree transformation will not be allowed. So actually, if you see that if you compare structure 1 and 3, if you see structures 1 and 3, then you will find that the red and yellow, they are occupying the same positions, and there has been one 180-degree transformation between the white and the black. See the black, white is up, black is down. Here black is up, white is down. So this is a 180-degree transformation. But for the red and yellow, there has been no transformation. So this 180-degree transformation is not allowed, and it will give you the structure of another molecule. Whereas two 180-degree transformations that I already showed you are allowed. So in the same way, let us consider some other examples. Now, if you look at the 2 and 3, that means if you look at this structure 2 and 3, then you will find that white and yellow, they are still occupying the same position, but I have made the transformation between the red and the black. See, I have interchanged the position of the red and the black if you compare 2 and 3. So this 190-degree transformation is not allowed. That means it will not give you the equivalent structure, but it will give you the structure of its enantiomer or another compound. But if we do two 90-degree transformations, now you see that if I compare 1 and the 4, I'll show you once again 1 and 4, rather 2 and 4, sorry. So here you see that red and black, they have been interchanged, and even the yellow and the white have been interchanged. If you do two 90 degrees transformations, then that is allowed, and that gives you the same equivalent structure. So hope you understood the concept behind the Fischer projections and the different transformations, and how to recognize which transformations are allowed, giving you the same equivalent structures, and which transformations actually give you a non-equivalent structure. Thanks for watching. Hope you liked the video. If you liked it, please give it a like and share it with your friends. Thanks a lot for watching.